All right, so we have already talked about in the past the idea of an integral, where an integral is the sum of your areas of your rectangles, and your rectangle was the height of the rectangle, f of x, times the base of your rectangle, which is dx, or delta x. And so it was just the sum of an infinite number of rectangles that filled up an area between the curve and the x-axis. That is going to be your integral definition, but what we want to look at today is going to be the limit definition of a definite integral, and using the correct notation with sigma notation for this. All right, so this right here is going to be your limit definition for an integral. And the other stuff on this page is going to be an explanation of the different parts of this, but this part right here is your limit definition. All right, so what we want to look at is this is the thing that we know right now. The integral from a to b, which is your lower bound and upper bound, of some function, whatever it may be, dx. Now, to think about this in terms of a limit, we're going to be using sigma, which means sum, which is your elongated integral, elongated s, for sum. So sigma is a sum going from k equals 1 up to n, and it's the limit as n goes to infinity. Well, what's k, what's n, and all this mess right here? All right, so f of c sub k, this looks very much like f of x, and delta x looks very much like dx. And in fact, they are the same thing, just a little bit different notation. So what the different parts tell us. N is going to tell you the number of rectangles that are being formed. All right, so let's think about this for a second. Not n going to infinity, but let's say that we had a sum going from k equals 1 to 4. What this would mean is that we are going to be filling up this space or region with 4 rectangles. All right, and right here we have f of c sub k times delta x. All right, so what this would give us then is we just start replacing k with 1 plus, because sigma means sum, f of c sub 2 times delta x plus f of c sub 3 times delta x plus f of c sub 4 times delta x. Now, what you'll notice over here is that we have the lower bound a, upper bound b. C sub k is going to be the breaking points for each of the rectangles in here. So C sub 1 would be the first segment for the rectangle. C sub 2 would be the next one, and if there are 4 rectangles equally spaced in here, C sub 2 would be at the halfway point here. C sub 3 would be located right over here, and then C sub 4 would be our last one over here on the end. Now, delta x then is going to be the distance between a and c sub k. It's going to be this little change in x right here. Well, how do we find that length for each of our rectangles? Well, we would find that by taking this value, b minus a, and then dividing that by the number of rectangles that we would have in here. For example, if A was at 2 and B was at 10, and we had 4 rectangles, 10 minus 2 is 8. 8 divided by 4 rectangles would be 2. So the base of each of our rectangles would be 2. And that would fill up that distance from A to B. So this right here, this B minus A divided by N, this is kind of a generic way of being able to find delta X. It's just the upper bound minus the lower bound, and then we're going to divide that by the number of rectangles. Okay, so we have our function at each of these values, C sub 1, C sub 2, C sub 3, and C sub 4. That's the height of the rectangle. This is the base of the rectangle, and this is how you find the base of that rectangle, B minus A divided by N. Well, C sub K, how do we find this value now? Well, like we said, we would take 10 minus 2 and then divide by N. That gives us delta X. So what we would do to find out where this first line is going to be located, we would take the A value and add the delta X to that. And that would give us the location for the first one. Now the second one, you would take the A value and add 2 times the delta X to give you the next one. And then the next line over here would be at the A value plus 3 delta X. And then the last one would be at A plus 4 delta X. So what we're doing then is we're taking C sub K is going to be equal to the lower bound plus K times delta X, where delta X is this right here. All right, so let's take a look at a problem and see how this plays out. The first thing that we want to do on these problems is we want to find the value of delta X. So recall delta X is B minus A divided by N. Our upper bound is 1 minus our lower bound of negative 1. And we do not know how many rectangles that we're making. And actually, when we write out the limit definition, it's going to be the limit as n approaches infinity, which means we're going to leave n in the notation. All right, so this comes out to be 2 over n. All right, so now we want to figure out, well, what is C sub k? All right, so C sub k, we said, is the lower bound, which is negative 1, plus k times delta x. And delta x in this particular problem is 2 over n that we just found from right here. All right, so let's figure out now f of x. Well, in this particular problem, f of x is this function right here. So f of x is x cubed. Now, if f of x is x cubed, that means f of c sub k would equal c sub k cubed, because all you're doing is taking this and substituting it in for x. But we don't want to put c sub k in here. We're going to take what c sub k represents in this problem, which is this right here. All right, so we're going to be taking this right here, substituting it into our function, which will give us negative 1 plus k times 2 over n. And I could also write this, I'm just going to go ahead and do that now, as 2k over n. and this is raised to the third power. All right, so if we go back to our limit definition, the limit definition said the integral from a to b of f of x dx is equal to the limit as n approaches infinity of the sum from k equals 1 to n of f of c sub k times delta x. Well, that means that our integral from -1 to 1 of x cubed dx would equal the limit as n approaches infinity from k equals 1 to n. Now, this part right here is this right here. All right, so we're going to bring this right over here. And then this part right here is our delta x that we have right here. So we're going to bring this part over here, which will give us times 2 over n. Okay? And so this would be your limit definition for this particular integral. All right, so next problem. Once again, first thing we want to start out with is what is delta x. So delta x is going to be the upper bound minus the lower bound divided by n, or in other words, 3 over n. We now determine c sub k, which is going to be the lower bound plus k times delta x, which is 3 over n, which would give us 1 plus 3k over n, which is what I'll use. Well, what is f of x? Our function is 3x squared. So the limit definition calls for us to use f of c sub k. Well, that tells us we're going to put c sub k, which is this, into x. All right, so that's going to give us 3 times 1 plus 3k over n squared. All right, so now let's build our limit definition. This integral would equal the limit as n approaches infinity, sigma going from k equals 1 up to n, of f of c sub k, where f of c sub k is this part right here, times delta x, which is this part right here. And that is our limit definition right there. All right, there's a few more of these, then you'll see that it really follows the same kind of pattern on all of them. So the first thing we're starting out with here is going to be determining what delta x is. So we're going to take upper bound minus lower bound divided by n, which is 2 over n. C sub k is the lower bound, 2, plus k times delta x, which would be 2 plus 2k over n. Now f of x is 2x plus 3. So f of c sub k we would get by taking c sub k, putting it in place of x. So what we're going to have now is going to be 2 times 2 plus 2k over n plus 3, which we could simplify this a little bit. This would be 4 plus 4k over n plus 3, which would actually become 7 plus 4k over n. All right, so building our limit definition then, this is going to equal the limit as n approaches infinity, sigma going from k equals 1 up to n. This part is going to be the same exact thing on every one of your problems. All right, so then we have f of c sub k, which is this part right here. And this is going to get multiplied by delta x, which is right up here. And that is your limit definition right here. All right, next one we're going to be looking at delta x being from e minus 1 over n, which cannot be simplified, so we're just going to leave it like this. C sub k then is going to be your lower limit, 1 plus k times delta x. And again, we'll just kind of leave it like this. That's all right. And then f of x is our function, which in this case is natural log of x. Therefore, f of c sub k we would get by plugging this into x, which will give us natural log of 1 plus k times e minus 1 over n. All right, so building our limit definition now, we're going to have the limit as n approaches infinity, sigma going from k equals 1 up to n of f of c sub k, which is this part right here, times delta x, which is this part right up here, and that is your limit definition right here. All right, and the last one we're going to work through here, delta x in this case is going to be upper limit minus lower limit divided by n. Well, we can simplify this a little bit. This would be 2/6 minus 1/6, which would give us pi over 6 over n, which is pi over 6n. All right, so c sub k is going to be your lower limit, pi over 6, plus k times delta x. So pi over 6n. Which becomes pi over 6 plus k pi over 6n. All right, so our function, f of x, is equal to sine of x. So when we find f of c sub k, like we've done before, we're going to take c sub k and plug it into x, which will give us sine of pi over 6 plus k pi over 6n. All right, so building your limit definition, this would be limit as n approaches infinity, sigma going from k equals 1 up to n. Again, what all this means is that we want an infinite number of rectangles. Okay? And then the part that comes after that is how you find the area of each one of your rectangles. And so You're going to have f of c sub k, which is this part right here, multiplied by delta x, which is this part right here. And that is your limit definition for this particular integral.